Hello and welcome back to Chapter 4, Part 2. Last time we talked about spectrum. We talked about the continuous spectrum, the absorption spectrum, and the emission spectrum. Then we talked about the atomic structure. And we finished with Planck's formula that gave us a relationship between the photon energy E and the radiation frequency F, and that formula was written as E equals hf. Just like the gravitational constant big G and the speed of light little c, Planck's constant is one of the fundamental physical constants of the universe. And this equivalence between the energy and frequency of a photon gave us the connection between atomic spectra and atomic structure. In this part, we're going to talk a little bit more about the details of what's taking place. If we see an absorption spectrum, it means that electrons within the atom are absorbing energy and they're moving up to a higher orbit or a higher excited state. Now I want to take a look at the simplest case scenario with the hydrogen atom. So think of a single proton and a single electron orbiting that proton. So when we have the absorption scenario, it means that the electron is absorbing energy, then can bump it up to a second or higher excited state. Once it does that, it will stay there momentarily within a few nanoseconds, and then it's going to jump back down to the ground state. And we call that decay. Now there's two ways of doing that. It could directly jump down to the ground state, or it could cascade one orbital at a time. So let's take a closer look at this scenario. In frame A at the bottom half of this slide, you see the scenario of direct decay. So the electron on the very left is absorbing a UV photon, an ultraviolet photon, that causes it to momentarily be excited and move on onto the first excited state. After about 10 nanoseconds, the electron is going to return back to its ground state, and in the process is going to emit a photon that has exactly the same energy as the original photon. So that's what's taking place in frame A. Let's take a look at frame B. What if the UV photon that's hitting this hydrogen atom has more energy? Well, if it has the right amount of energy, it could bump up our electron into a higher excited state, for example, the second excited state as shown in the middle. If we take a look at the top scenario then, the electron could fall immediately back down to the ground state, emitting a photon identical to the one it absorbed. If you look at the bottom scenario though, the electron could initially fall into the first excited state, which will produce a visible radiation photon of wavelength 656.3 nanometers. This corresponds to hydrogen alpha transition, which is the characteristic red glow of excited hydrogen. Then the electron is going to emit another photon to jump down to the ground state. So this photon is going to have the same energy as in part A as it falls back down to the ground state. The object shown in the inset is an emission nebula, and its designation is N81. It is basically an interstellar cloud, which is mostly made of hydrogen gas that is excited by absorbing radiation emitted by those hot stars, those little white areas shown in the center. So this nebula is in front of the stars, which is blocking our view from our point of view. So the hot stars are emitting radiation. The hydrogen gas gets excited by absorbing this radiation. So the end result that we see is the emission nebula called N81. So we can have the absorption spectrum when atoms, the electrons within those atoms, absorb photons of the right amount of energy, the right quanta, in order to be excited to higher orbits, to higher states. Now, that was the simplest scenario using a hydrogen atom, but of course we could have atoms that have lots of electrons. The end result would be a much more complicated spectra because we would have many more possible states of transition. If we take a look at frame A right there, that is a helium atom in its ground state, you see two electrons occupying the lowest energy orbital, or the ground state, and they're orbiting a nucleus that contains two protons, the ones that are labeled with the plus, and two neutrons, the ones that have no charge. On frame B, we see a carbon atom in its ground state. We have 6 electrons orbiting a 6-proton and 6-neutron nucleus. And as you can see, 2 of the electrons are in the inner orbital, and the other 4 are at a greater distance from the center. Emission lines can be used to identify atoms. So when we take the spectrum of this emission nebula, we should be able to tell what it is made of. This is a picture of the visible spectrum of the Omega Nebula designated M17. It is shining by the light of several very hot stars. The gas in the nebula then produces a complex spectrum of bright and dark lines shown in the bottom. And of course, that same spectrum can be displayed as a wide graph of intensity versus frequency that spans the visible spectrum from red to blue. Now, the word nebula in general just means gas cloud. It is a site where new stars are forming. Now, what if we have molecules rather than just atoms? Well, molecules behave in a more complicated manner because they can vibrate and they can rotate. And that can cause a lot more complicated scenario, which in turn results in a more complicated spectrum. Electron transitions produce visible and ultraviolet lines. So if you take a look at part A, this is a molecule carbon monoxide, or CO, and on part A is undergoing a change in which an electron in the outermost orbital of the oxygen atom drops to a lower energy state, emitting a photon of shortest wavelength in the visible or ultraviolet range. We could have what's called a vibrational transition, and that produces infrared lines. If you take a look at frame B, we have illustrated here a change in vibrational state, which happens at the intermediate wavelength, so it gets released an infrared photon. And we could also have rotational transitions, which produce radio wave lines, and that is illustrated in frame C, where it shows a change in rotational state of longest wavelength, which results in the radio range. So molecular spectra are much more complex than atomic spectra, even for hydrogen. In frame A, you see the emission spectrum of molecular hydrogen. Notice how it differs from the spectrum of the simpler atomic hydrogen illustrated in frame B. Let's talk a little bit more about spectral line analysis. If we analyze the spectrum of an object, we can gather information on its chemical composition, its temperature, and its radial velocity. Now look at the picture on the bottom, the hydrogen alpha, hydrogen beta, and hydrogen gamma emission spectrum. Because of the Doppler shift, the entire spectrum of a moving object can be shifted to higher or lower frequency. The spectrum at the center is the unshifted emission spectrum of pure hydrogen. So this corresponds to the object being at rest, which is why we have 0 kilometers per second shown right there. On the other hand, the top spectrum shows the slight redshift of the hydrogen lines from an object moving at a speed of 300 kilometers per second away from the observer. So notice how, because the object is moving away, we have a Doppler redshift. So all the lines have shifted towards the red, towards the left in this case. Once we recognize the spectrum as that of the hydrogen atom, we can identify specific lines and measure their shifts. The amount of the shift, in this case 0.1%, tells us the object's recession velocity, 0.001, the speed of light. The spectrum at the bottom shows the blue shift of the same set of lines from an object approaching us at 600 kilometers per second. The shift is twice as large, 0.2%, because the speed has doubled. And in the opposite sense, because the direction has reversed. We can also have what's called a line broadening of those emission lines within the spectrum. If you take a look at the picture on frame B of intensity versus frequency, notice how we no longer have a sharp spike, but we have more of a broadening of the peak. By tracing the changing brightness across a typical emission line, as in frame A, and expanding the scale, we can obtain a graph of the line's intensity versus its frequency, as shown in part B. Now, table 4.1 right here summarizes the spectral information that can be derived from observing star light. Peak frequency or wavelength of continuous spectra can give us the temperature once we use Wien's law. The actual lines present in the spectrum can give us the composition. The same with the line intensities. We can derive the composition of the light, what it is made of. The line width in itself can give us information on temperature, rotation speed, density, turbulence, even the magnetic field. And the Doppler shift observed can give us information on the line of sight of velocity. Remember, line of sight because Doppler shift takes place on the radial line of velocity. The Doppler shift may cause thermal broadening of spectral lines. in frame A, you see atoms moving randomly, and they produce broadened spectral lines. On frame B, you see as their individual red-shifted and blue-shifted emission lines merge together, and the end result that we would see in our detector. Now, the hotter the gas, the greater is the degree of thermal broadening. Rotation also causes broadening of the spectral lines through the Doppler effect. The rotation of a star can cause spectral line broadening. Because most stars are unresolved, that is, they're so distant that we cannot distinguish one part of the star from another, light rays from all parts of the star merge to produce the broadened lines that we see. The more rapid the rotation, the greater is the broadening. So if you take a look at the inset right there, if the broadening is very, very small, then we know that this object is not rotating rapidly. If the broadening line is very, very big, then we can tell that this object is rotating very rapidly. And this brings us to the end of Chapter 4. Here's a small summary of Chapter 4. A spectroscope splits the light beam into component frequencies or wavelengths. A continuous spectrum is emitted by solid, liquid, and dense gases. A hot gas has characteristic emission spectrum. A continuous spectrum incident on cool, thin gas gives us a characteristic absorption spectrum. The spectra we see can be explained using atomic models with electrons occupying specific orbitals. Emission and absorption lines result from transitions between these orbitals. Molecules themselves can also emit and absorb radiation when making transitions between vibrational or rotational states. So please study Chapter 4.3 through 4.5. Review the formation of spectral lines, the basic model of the atom, electron transitions, and the spectral information that can be obtained from starlight. Chapter 4 concludes our introductory chapters. Once you study Chapter 1 through 4 carefully and you understand what's taking place, the chapters that come after this will make a lot of sense, because we're going to use all this information we learned right here on the basics to explain stellar evolution and cosmology. Until next time.